Hello and welcome to the lecture of coordination chemistry. In this lecture, as I told you in the previous lecture, that we'll talk about the metal ligand bonding, and one of the way to explain the metal ligand bonding is HSAB concept, that is hard soft acid base concept. So we can classify acid or base into two classes. So we can classify acid or base into two classes. One is hard, another one is soft. Okay, that means you have these combinations. So you have these combinations. You can have hard acid, hard base, soft acid and soft base. Okay, now what this HSAB principle, that is hard soft acid base principle, is saying us that hard acids prefer to combine with hard base and soft acid prefer to combine with soft base, or vice versa. That means hard base prefer to combine with hard acid and soft base prefer to combine with soft acid. Fine. So this is what HSAB principle is all about. Okay, so HSAB principle is telling us that hard acid prefers to combine with hard base and soft acid prefers to combine with soft base and vice versa. That means hard base prefers to combine with hard acid and soft base prefers to combine with soft acid. Okay, so that means, so as I've discussed in the previous lectures, that you can consider hard acid means metal and base means ligand. That means what HSAB principle is telling us that metal, if it is hard, so when we are talking about hard metal and it combined with hard ligand, or you can say you have soft metal and you have soft ligand, that means hard combination and soft combination. That means this will lead to stable coordination compound. This will lead to stable coordination complex. But if you take the combination of, you can consider hard metal plus soft ligand, or you say soft metal you have and you have hard ligand, that means you have hard soft combination. But according to HSAB principle, this will lead to unstable coordination compound. That means hard metal and soft ligand, or soft metal or hard ligand, will not lead to a stable coordination compound. But what HSAB principle is telling, that if we take hard metal and it combines with hard ligand, or if you take soft metal and it combines with soft ligand, then that will lead to stable coordination complex. Fine. That means what we can say is that hard combination and soft combination is more preferable than hard soft combination. That is what HSAB principle is telling us. Okay. Now when we are talking about hard and soft, that means hardness or softness, we have to define. Now hardness or softness you can explain from charge density also. So from charge density. Fine. Now what is charge density? Charge density means charge by size ratio. Charge to size ratio is what charge density is. Now if the charge density is higher, in that case we can say it is hard. That means if this charge density increases, that means we can say hard character increases. That means hardness increases. Fine. Now if this charge density decreases, we can say soft character, that is softness, increases. Okay, so from charge density we can explain what is hardness and what is softness, what is hard, what is soft. When I am saying charge density is increasing, hardness is increasing, that means either the charge is increasing or the size is decreasing. In that case hardness will increase. Now if charge is decreasing and size is increasing, in that case softness will increase. That means soft character will increase. Fine. Okay, now you have, so what we are talking about, we have acid and base. This acid and base you can classify into two category, hard you have and you have soft. That means you can have four category, as I have earlier told. So you have these four category. So hard acid and soft acid, hard base and soft base. Now hard acid and soft acid both are what? Accepted. These are acceptor atom, and when you are talking about hard base and soft base, that means it is the donor atom. Fine. Now we'll see with examples of these four categories: hard acid, soft acid, hard base and soft base. Fine. So let's start with hard acid. Hard acid, that means it is acceptor atom. Fine, it is acid means acceptor. So this is acceptor atom that is marked by, you can say hard means size is less. Fine. Okay, so hard acid is that acid where the acceptor atom is marked by the less size, the high positive oxidation state, or absence of any outer electron which are easily excited to higher states. So if these conditions are satisfied, then we can say that the acceptor atom is a hard acid. Okay, so or the metal is a hard metal. Okay, now if you take the example of hard acids, then I'm writing the examples of hard acids. So you have H plus, you have Li plus, you have Na plus. Okay, so these are the examples of hard acid. So the example of hard acids are H plus, Li plus, Na plus, K plus, Be2 plus, Mg2 plus. This I have written down for you. And the ions which has oxidation state greater than 4 or greater than 4, that can be classified as hard acid. And also HX, that means hydrogen bonded molecules, are also under the category of hard acid. Okay. Now next, move into the soft acid category. Now acid, that means it is also an acceptor atom, but it is soft. That means acceptor atom is marked by large size, you can say, Then so soft acid is characterized by the soft acid is where the acceptor atom is marked by large size, zero or low positive oxygen state, and it has several easily excitable valence electron. Then in that case we can say the metal is soft metal, or you can say it's a soft acid. Now if you see the example of soft acid, so these are the examples of soft acid: Cu plus, Ag plus, Au plus, Tl plus, Cd plus, Cd2 plus, Pd2 plus, I plus, Br plus, Cl2, Br2, I2, metal with zero oxidation state. Okay, as I've said, zero or low positive oxygen state is a characteristics of soft acid. And you have the trinitrobenzene. So these are the examples of soft acid. And there is a third category also. If you see, there are also some atoms, or you can say group of atoms, which are not that hard and which are not also that soft, that are in between, and that we call as borderline. So that is what borderline. So not so hard and not so soft. Okay, so these are in the borderline, not so hard, not so soft. So if you see the example, then you have BMe3, Fe2 plus, you have cobalt 2 plus, you have nickel 2 plus. So these are the examples of borderline: BMe3, Fe2 plus, CO2 plus, Ni2 plus, Cu2 plus, Zn2 plus, Pb2 plus, like this. Okay, now we will see the base, that means the donor atom. So first let's see the hard base. Hard base means base it is, so it is donor atom. Donor atom. So donor atom is characterized by the following. Then we can say it is hard base. So hard base, that means it is donor atom, and the donor atom is characterized by high electronegativity, low polarizability, and the presence of field orbitals. And if field orbitals is not present, then in that case empty orbitals, but that empty orbitals may exist at high energy level. So these are the characteristics of hard base. Okay, now if you see the example of hard base, so if you see the example of hard base, that means base that is ligand, hard ligand, then H2O, H minus, F minus, Cl minus, CH3, CO2 minus, NO3 minus, CO3 2 minus, ClO4 minus, OR minus, like this, N2H4 or NH2. These are the example of hard base. Okay. Now if you see, you have soft base. Okay. Now you have soft base. Now base means it is a ligand, that means donor atom. The donor atom is characterized by the following, then you can say it is a soft base. So the characteristics of soft base, or you can say soft ligand, are the following: low electronegativity, high polarizability, or partially filled orbitals or empty orbitals, but that should be low lying. Okay, so these are the characteristics of soft base or soft ligand, you can say. Now if you see the example of soft base, then you have H minus, I minus, HCN minus, CO, C2H4, RS minus, R3AS, okay, RSH, so H2O3, 2 minus, okay, now R3P, so H minus, I minus, HCN minus, CO, C2H4, RS minus, R3AS, RSH, H2O3, 2 minus, R3P. So these are the examples of soft ligand or soft base, you can say. Now as I have earlier said that in between hard and soft you have borderline. So you have borderline ligand also. We have seen borderline metal earlier. So borderline, you can say. So these are the example of pH, NH2, you can say, or you can say N2. So these are the examples of borderline ligand: pH, NH2, N2, NO2 minus, Br minus, like this, etc. Okay. Now if you see very closely, if you observe very closely the hard acids, soft acid, hard base and soft base, then you can classify the metals into two classes. First you have class A metal and class B metal. If you classify, if you closely observe the examples of the metals of hard acids and soft acids, acid means metal. Now if you see the example of hard acid and soft acid, then you can classify the metals into two classes, class A and class B. Now under class A you have Now under class A you have Na plus, K plus, Ca2 plus, Fe3 plus, CO, cobalt 3 plus, etc. That means you have alkaline earth metal, and you have the high positive oxidation state of the first row transition metal. Now if you closely observe the examples as I have discussed so far, then these kind of metals which are categorized under class A metals, these are generally hard in nature. So these are generally hard. That means this hard metal will prefer to combine with hard base, that means with hard ligand. Now hard ligand, that means in the ligand the atoms will be N, O, F. Okay, so if you see the stable coordination complexes of Na plus, K plus, Ca2 plus, Fe3 plus, cobalt 3 plus, then you see that these are hard acids. These are hard acids. That means it will prefer to combine with hard base. That means that hard base will have the liganding atom as NOF, because these are also hard. Fine, hard atom, you can say. So the ligand consisting of N, O and F atom will prefer to combine with Na plus, K plus, Ca2 plus, Fe3 plus, cobalt 3 plus. Okay. Now under class B metal you have the examples of okay, so these are the examples of class B metal: Cu plus, Ag plus, Ag2 plus, Pd2 plus, Pd, 2 plus. That means these are soft in nature. These are soft metals. Okay, so that means these are soft acids. So these will prefer to combine with soft base, or you can say soft ligand. That means that ligand which has soft metal atom attached with this. That means you have P, S and Cl. That means the ligand attached with the donor atom, where the donor atoms are P, S or Cl. That means these are soft in nature. Now we know that soft combination is preferred. Soft combination will give rise to stable coordination complex. That means the ligand which consists of these metals P, S and Cl, so this will prefer to combine with these kind of metals Cu plus, Ag plus, Ag2 plus, Pt2 plus, that we have classified as class B metals. So if you closely observe the examples of hard acid, hard base, soft acid and soft base, then you can classify the metals into two categories, class A and class B. Under class A category, there are Na plus, K plus, Ca2 plus, Fe3 plus, cobalt 3 plus. These are there. That means these are hard metals. Now you know from the HSAB principle that hard metals prefer to combine with hard ligand. Okay. Now hard ligand means the ligand consisting of N, O or F atoms. Okay. That means under class A category, these are the metals and these prefer to combine with the ligand which consists of N, O or F atom. Now under class B, you have these kind of metals Cu plus, Ag plus, Ag2 plus, Pt2 plus. So these are soft metal. That means according to HSAB principle, these soft metals will prefer to combine with soft ligand. That means soft ligand means the ligand which consists of PaCl atoms. Okay. So if you see the hard soft acid base theory, hard soft acid base principle, then this hard soft acid base principle is largely based on observation. That means it's an empirical rule. So the HSAB concept is largely based on observation. You can say it's an empirical rule. Okay, and the theoretical basis of HSAB principle is still not understood very clearly, but you can get a general idea that hard combinations are preferable due to strong ionic force. You can understand. So it's a very general idea. Strong ionic force, you can get an idea. And soft combinations are preferred according to HSAB principle, maybe due to the London dispersion force. But again, the theoretical basis of HSAB principle is still not clear, is still not understood fully. Okay, so it's an empirical rule which is largely based on observation. Fine. So what is the usefulness of this HSAB principle? Let's understand one by one. So we will read now the usefulness of HSAB principle. So the main usefulness of HSAB principle is that it can predict the stability of many complexes. So HSAB principle is mainly helpful in explaining or predicting the stability pattern of complexes. If you see the example, then the CO, which CO means it's a soft ligand, it is soft in nature. Now CO, as it is soft in nature, that means it will prefer to bind with soft metal according to HSAB principle. Now if you see NiCO whole 4, then it is a stable complex, this you know. So the stability of NiCO4 can be explained in terms of HSAB principle. So you have CO, which is a soft ligand, Ni is in Ni0 state, that means it is also a soft metal. That means soft combination is giving rise to a stable coordination complex. That means you can predict the stability pattern of a complex by using HSAB principle. That means you can understand that as CO is a soft metal, that means it has always a tendency to combine with a metal which has zero or very low positive oxidation state. Low positive oxidation state. Fine. Okay. Now if you see the other examples, then you have seen that for the extraction of AgAU, so for the extraction of AgAU, we use cyanide method. We generally use cyanide method. Now you know cyanide Cn minus is soft ligand. It's a soft ligand, and if you see the Ag plus or Au plus, it is also soft metal. That means soft combination is there. That is why Ag and Au extraction is done by cyanide method. So this you can explain why Ag and Au is extracted by cyanide method. You can explain this from HSAB principle, because there is soft interaction between the metal and the ligand. Okay. So Cn minus is soft, Ag plus Au plus is also soft. Okay. Now the next example you can take is that you can predict the order of stability of FeX6. So FeX6 3 minus, where X is FCl Bri. Fine. That means if you are asked to tell the order of stability, so if you are asked to write down the order of stability of FeX6 3 minus, where X is FCl Bri, then you can do it by using HSAB principle. So if you see this FeX6 3 minus, then here Fe is in plus 3 state. Now Fe is in plus 3 states, that means it is a hard metal. It is a hard metal. Now if you see F minus is also a hard ligand. It is very hard, very high electronegative F minus. And I minus is very soft ligand. That means Fe3 plus will prefer to bind with F minus, and that will give rise to stable coordination complex, stable complex. That means if you see the stability pattern, then FeF6 3 minus will be most stable. Then FeCl6 3 minus, then FeBr6 3 minus, and then at the end FeI6 3 minus. So this will be least stable, because I minus is a soft ligand and it is combining with a hard metal Fe3 plus. That means that will not give rise to a stable coordination complex. That means FeF6 3 minus is the most stable here, because Fe3 plus is a hard metal and F minus is also a very hard ligand. Fine. So it can, we are observing that the hard soft acid base principle is useful in explaining the stability of many complexes. If you see the other example, chromium NH3 whole 6 3 plus is stable. So it is stable because if you see the chromium, then chromium is in plus 3 states. That means it is hard, and NH3 ligand is also very hard. That means hard combination is giving rise to a stable coordination complex. But if you see the example of CrCO whole 6 3 plus, then it is not that much stable, not stable, because Cr3 plus is a hard metal, but if you see the CO ligand, then it is soft in nature. That means it is the hard soft combination, but hard soft combination according to HSAB principle is not preferred. That means this CrCO whole 6 3 plus is not a stable complex. Okay, but CrNH3 whole 6 3 plus is stable. So that means you are observing that this HSAB principle is useful in giving an idea, in explaining the stability of coordination complexes, that why these complexes are stable, why these complexes are not stable. Now you can also use this HSAB principle to explain the solubility trend. So solubility trend. Okay, now if you see the example of LIX and AGX, where X is FCl Br and I, fine. So X is FCl Br and I. So by using HSAB principle, we will try to explain the solubility trend of LIX and AGX, where X is FCl Br and I. Now if you see LIX, here Li is in plus 1 state. Okay, so Li plus, the size is very small. This is a hard metal. This is hard. Okay, so this is hard. Now when the X is F, that means F minus is the hardest ligand, you can say, it is very hard. And in case of AGX, Ag is in plus 1, so Ag is very soft, and I minus is very soft. Okay, now when we are talking about solubility, we are talking about solubility in water. Now water is a hard ligand, water is also a hard ligand, but water H2O is not that hard as F minus. So if you see the hardness, then F minus is greater than H2O, if you see the hardness pattern. So when the LIX is dissolved in water, in that time the Li plus, as it is hard, it will prefer to combine with harder F minus than H2O, because H2O is hard, F minus is also hard, but F minus is more harder than H2O. That means Li plus will prefer to combine with more hard F minus. That means Li plus will prefer to combine with F minus and not with H2O. As Li plus will prefer to combine with F minus and not with H2O, that means the solubility of LiF will be least, because it is not combining with H2O. But if you see the LiF, then Li is very hard and I minus is very soft. That means Li plus will not prefer to combine with I minus, rather Li plus will combine with H2O. Okay, that means Li is, it has maximum solubility, because Li is not combining with I minus, Li plus is combining with H2O. Now if you see the AgX case, the reverse case is happening, because Ag plus is a soft metal. As Ag plus is soft and H2O is hard, now when it has, Ag plus has the option that it has I minus, which is very much soft in character, then Ag plus will prefer to combine with I minus rather than H2O. That means when Agi, you are talking about Agi, that time Ag plus will prefer to combine with I minus rather than H2O. That means Ag plus is not combining with H2O, so Agi has least solubility. Okay, but if you see the AgF, then as Ag plus is very much soft, but F minus is also hard, H2O is also hard, but F minus is more harder than H2O. That means Ag plus will combine with H2O. Okay, so as Ag plus is combining with H2O, that means AgF will have maximum solubility. Fine. So by using HSAB principle, you can predict, you can explain the solubility trend of complexes. Okay, fine. Now I will tell a concept which is called symbiosis. So now we'll talk about symbiosis. Okay. Now when we are talking about hardness and softness, this hardness and softness is not absolute. That means it is a relative term. This hardness and softness is not an absolute term, it is a relative term. So hardness and softness character is not absolute, is a relative term. So hardness and softness character is not absolute, it's a relative term, and the hardness or softness of the metal can be altered, can be changed by the influence of the ligand atom present. So hard and soft character is not an absolute term, it's a relative term, and the hard and soft character of the metal ion can be affected by the other ligand that is attached, that is present in that complex. Fine, and this change in the soft or hard character, this we call it as symbiosis. This is what we call as symbiosis. That means the change of the character of the metal ion due to the influence of the ligand that is present with it, that is what we call symbiosis. So what is symbiosis? Hard and soft character of metal ion can be affected by other ligand that is present in that complex, and this phenomena we call it as symbiosis. Fine. Now this will be clear to you and I will give you the example. So if you take the example of cobalt NH3 whole 5 X and you have plus, so here cobalt is in +2 state. Fine, cobalt is in +2 state means it is soft, you can say. Okay, you can soft or borderline soft. Okay, and that means as CO2 plus is soft, now X is F minus, Cl minus, Br minus and I minus. Now you have to tell when this CONH3 whole 5 X plus will be more stable and when it will be least stable. Okay, now you have CO2 plus, it is soft or borderline, it is soft in nature. Okay, now as CO2 plus is soft in nature, then at the first glance you can predict that as CO2 plus is soft in nature, so X, when X is equal to I minus, in that case this complex will be more stable, but this is not the case. When X is F minus, in that case this complex is more stable. When X equal to F minus, then this complex is more stable. Now why this is so? So why? This is due to symbiosis, because if you see CO NH3 whole 5 X, here CO2 plus, although it is soft, that means you can understand from HSAB principle that soft metal will attract soft ligand, that means X should be I minus, but when X is F minus, that means when X is a hard ligand, in that case this complex is more stable because here symbiosis occurs. In this complex 5 NH3 ligand is present. Now NH3 is very hard, so NH3 is very hard and there are presence of 5 NH3 ligand. Now due to the presence of 5 hard NH3 ligand, this cobalt, this metal will attract hard ligand. So what I am telling, due to the presence of 5 hard NH3 ligand, the metal will attract the hard ligand. As the metal will attract the hard ligand, that means when X is equal to F minus, in that case this complex will be more stable. Now if you go by the simple HSAB principle, then in that case, as cobalt as the metal is soft, so when X is I minus, that means when the X is very much soft in nature, in that case the complex should be stable. But as I have said, the hardness and softness of the metal is not an absolute term, is a relative term, and the hardness and softness of the metal can be influenced by the ligand that is attached with it. Now here there is presence of 5 hard NH3 ligand. So due to the presence of 5 hard NH3 ligand, the metal will attract the hard ligand. Okay, and so when X is equal to minus F, so X is F minus, then in that case this complex will be most stable. Now let's take another example. So if you take another example, okay, if you see this example and you have to tell when this complex is most stable. Okay, if you see here, the cobalt is in +3 state. Okay, so a cobalt is in +3 state, that means it is very hard. So it is hard in nature. So if you go by simple HSAB principle, so as cobalt 3 plus is hard, that means it will prefer to combine with hard ligand. That means X should be F minus. So when X is equal to F minus, in that case the compound will be stable. But this is not the case. When the X is I minus, that means when the ligand is soft, in that case this complex is stable. Why? Again here the case of symbiosis. Now see, the cobalt CN5 X 3 minus. Fine. Now cobalt is in +3 state, that is hard. But here 5 Cn minus is present. Now Cn minus is very soft ligand. Now as we have seen in the previous case, due to the presence of 5 hard NH3 ligand, the metal will attract the hard ligand. In this case also, due to the presence of 5 soft Cn ligand, the metal will attract the soft ligand. So X will be soft, and in that case the complex will be stable. So when X is equal to I minus, because I minus is very much soft, in that case this complex will be most stable. Fine. So this is symbiosis. Symbiosis is clear to you. Now I just want to make one point and then I will end this HSAB principle, is that what we are explaining, we are explaining the stability of the complexes, we are explaining the solubility pattern, but these are very general idea. So when we are explaining the stability when we are explaining the stability of the complexes, solubility trend by HSAB principle, then you have to also understand that this is one of the way of explaining the stability pattern or solubility. There are many other factors beside HSAB which can explain the stability factor, which can explain the solubility factor. So HSAB principle is a very general idea that can explain the stability order, that can explain the solubility order. But you have to understand there are also many other factors which are involved in the stability of the complexes, in the solubility of the complexes. We are mainly focused on in this lecture about HSAB principle. That is why in explaining the stability of the complexes, in explaining the solubility pattern of the complexes, we are using the HSAB principle. But so you have to understand that HSAB principle is not the only factor which can explain the stability or solubility of the complexes. It is one of the way of explaining the stability or solubility of the complexes, but there are many other factors which are also involved in the stability or in the solubility pattern of the complexes. Fine. Okay, that means that if I give you one or two examples, then it will be clear to you that it is a very general idea and it is not a foolproof idea. If you see if you know Fe3 plus, Fe3 plus is very hard in nature and HCN minus is soft. But if you see, the Fe-HCN complexes are stable in nature, are stable. That means hard and soft combination are giving rise to stable complexes, which you cannot explain from HSAB principle. Then again, if you see this complex AgNH3 whole 2 plus, then Ag plus is soft, NH3 is hard. That means according to HSAB principle, this compound should not be stable, but in reality this compound is stable. That means you can understand that yes, HSAB principle is important to us. It can explain many stability pattern, many solubility pattern. Okay, but you have to understand this is very general. This is not a foolproof idea. It cannot explain all the metal ligand bonding. If it were able to explain all the metal ligand bonding, then there was no need of the other bonding theories. Okay, so you can understand that yes, it is helpful in predicting the stability of the coordination complex, in predicting the solubility pattern, but it is a very general idea and it is not foolproof. So it is a very general idea and it is not foolproof. So if you summarize what we have discussed today, then in HSAB principle, we have at the very beginning we have told that we are classifying the acid and bases into two classes, hard and soft. Then we have seen what is the principle is saying, that hard combination, soft combination is preferable. And then we have seen the characteristics of hard acid, hard base, soft acid, soft base. We have seen the examples. Then we have seen what is the importance of HSAB principle to us. It is helpful in explaining the stability pattern, the solubility pattern. And then at the last we have also talked about what is symbiosis. Then we have also seen that this HSAB principle is not foolproof. It is a very general idea. That means it has its drawback also. So that's it for today's lecture.